Recorded is rolling. It is Wednesday, January 11th. We're going to do this oscillating spring lab today. This is on the same paper that you guys did the pendulum lab on. It's just printed on the opposite side. So, I know there's a few 10th graders in here. I know you guys were testing yesterday. So here, I tell you guys what we did. So we finished the pendulum lab yesterday. Took about first 2 minutes of class. We linearized the motion of the graph. So like it was time period squared versus length, or time period versus the square root of the length. Either of those would linearize the graph. Just like this right here, it all fed into this. Right, so make sure you have the skill to go from this equation to this graph. And today we're going to do something extremely similar. I mean, the structure is the same, right? So instead of a pendulum swing back and forth, now it's just we're going to put this mass on this spring, right? And it's going to just oscillate up and down, right? So really similar structure. I'm going to put that formula. And also yesterday we did a bunch of demos. Some of the demos were related to harmonic motion. And then some were related to waves. All the wave stuff is not going to be on the AP exam. That used to be, but it's not anymore. All right, so we're just going to mostly focus on oscillation type stuff. All right, so the goal of this lab is going to be, can you figure out what the spring constant is of the spring, right? So spring constant is like how stiff is the spring, right? And the first time you guys saw spring constant was related to Hooke's law. You guys remember Hooke's law? Okay, if you put a force on a spring, it will stretch it. Right. And then how much it stretches it depends on how stiff the spring is, right? For some given force. Right? Or compress. Now these springs aren't going to compress, but it would work the other way if you have like a compressible spring too. Right? So sometimes you see that, but these are just kind of stretch. Okay? But now there's another formula that also has spring constant in it, and that's the oscillating spring formula, right? So be able to navigate Hooke's law. Hooke's law is just F equals Kx, right? Very simply, F equals Kx. But the other one here is this one. This is on your AP equations. I pointed this out to you guys yesterday. Both of these guys are next to each other. Boom, right here and here on your AP equations that you're allowed to use on the actual exam. Okay? But good to know those, you know, especially if you've used them so much that you just know them by heart just because you've used them so much and apply them so much, right? Okay. And one of the skills I really want you to have, you need to have the skill going into the AP exam in a few months, right? Is to be able to go from a formula like this to linearize it and be able to interpret the slope. Okay? Now, this is not the only way to linearize this particular formula. So let's, one of the things I want to do before I send you back to the lab area to try this out with your teammates is to go through like different options that you could, there are like multiple ways you could linearize that formula and get the spring constant from it. Right, so this is going to be a two-part lab. The first part, like this table and these graphs, the idea is I want you guys to follow Hooke's law, just F equals Kx. Right, let me write that up. So you guys know Hooke's law, just the force on the spring equals K times X, where K is the spring constant, how stiff the spring is. That's the goal of this lab, figure out what that is. And X is like how much it's stretched from its original like unstretched position. Okay. And then of course you guys have this new one, this oscillation. Time period equals 2 pi times the square root of the mass divided by the spring constant, right? Where the mass is whatever I hang on it, right? One of the assumptions, one of those little details that it's going to show up, right, is that you're assuming, like one of your assumptions, simplifying assumptions, is that whatever the mass is that you're hanging on it is very large compared to the mass of the spring scale, the mass of the spring. Sometimes we'll say the mass of the spring is negligible, right? You might hear something like that. Mass of the spring is negligible. Right. So some other things about this. Right? So suppose you're starting off with just hanging out the spring just like this, just hanging by its own weight, which is hardly anything. So it's just not going to move very much. Okay? Now, what if you put this on here and you let it very slowly come to rest, or what if it oscillated for a little bit and then eventually came to rest? That would be like an equilibrium position. Isn't that like that third picture, like equilibrium position, right? Versus what if you started from here and then you just dropped it and it like overshot the equilibrium position and then it oscillated back and forth for a little bit, right? So I wonder like how much is it going to overshoot it? Like what is the maximum stretch value compared to the equilibrium stretch value. Okay? And I want to show you guys that it's always twice the value. Like this is always 2 times this, right? That's one of those little tidbits that could totally pick you up a couple of points somewhere in the AP exam, maybe in the multiple choice section, something. Oh yeah, I remember that. That's gonna be the. I can prove that to you guys. Okay. So this one is a little bit simpler. So let's start with this one. This is just Hooke's law, F equals kx. Let's start from that. So this x is actually x equilibrium for like that third picture. Let's start at x equilibrium. So there's some weight on it, which is could be mg, right? Mg could be the weight pulling down. K times x equilibrium. Okay. Okay, let's solve for x equilibrium. Oh, it's one step. You just divide the spring constant down. Okay, so that x equilibrium is going to be whatever weight divided by the spring constant. Okay. So what I'm trying to show you guys right now is that this is always going to be twice of this. So this value is mg divided by k. Okay. So this one should be 2 times that. Okay. Now how am I going to show that? Well, guys, if you start off just holding this up here, so right, and then let it go, and it stretches maximally. What framework in physics do you think I'm going to use to solve that? And it's not Hooke's law, and it's not oscillation. So a few months ago. So you have changing height, changing spring, energy, right? Energy conservation. Okay. Because when this mass is all the way up here, what kind of energy? Gravitational potential, right? And as it falls, that probably converts to more kinetic. But oh, how much kinetic is there at the very bottom? 0, because it's maximally stretched. So there's no kinetic at the top, there's no kinetic at the bottom. Where'd all the energy go?
Spring potential.
Into spring potential. So we're going from gravitational potential to spring potential, right? You guys see that? Okay. Hey, can you guys set up a conservation of energy and beat me to the answer? Okay. Trying to give you guys a little bit of head start here. Sum of energy initial equals sum of energy final. Ooh, what would be in the closed system to make this work? Maybe the weight and the earth, right? Yeah, in the spring, right? Spring weight earth system, right? So what did you guys put for this part? MGH, right? But instead of H, isn't H like the maximum stretch? If you define height 0 down here, you're right, it would be MGH, but instead of H, I'm going to say X max, right? MG X max. Okay. And then what did you guys put for this term? 1/2 kx squared. Hey, is this x? This is x, the same x. Yeah, this is how much it stretched. This is how much it stretched too. It's the same x. Oh, so is one of those going to cancel on both sides? Right, same x, right? Guess that. Get rid of that square. Okay. And then see, like before with Hooke's law, it was just hanging in equilibrium at rest. Solve for x that way. Okay. So here, let's see, I'd have to multiply over the 2. So that's 2 mg, divide the k down. And oh, look at that. Just like I promised you guys. You guys see how the maximum stretch is twice the equilibrium stretch length, right? Right. Okay, you guys see that? It's the same thing, just factor 2. Right, so yeah, what that means is if you just drop it from rest, it's going to overshoot the equilibrium and oscillate back and forth a bit. If you look at that maximum stretch compared to where it eventually comes to rest, this is going to be twice this. Okay. All right, so that's a little side experiment, a little side thought there. Okay. Right. Before I send you guys back here, I want to look at different ways you could linearize this. You know what I really wish I did not do? I hate that I did this, is I labeled these axes. I should have left these axes blank because there's multiple ways you could go about this. So let's go through multiple ways you could actually solve this oscillation. So let's start with time period equals 2 pi times the square root of m over k. Okay. Now the way we went through the pendulum lab, which had again very similar looking formula, is we were doing like a caveman approach. We said we don't know how anything works. We have a stopwatch and go figure everything out. Okay. The way we're doing this one is like the opposite perspective. We're saying we know what the formula is. Okay. Can you what would you do to like linearize graph, right? Which is something that AP likes to ask on FRPs. Okay. In multiple choice too. Sometimes you see that. Okay. So if your goal is to figure out k, can you guys rearrange this somehow so that k shows up in the slope, and you can take the slope and do something to solve for k? Right? There's multiple things you can do. So okay, let me give you guys a little bit of a head start. Figure out at least one way, and then I'll take you guys through multiple ways. Figure out one way. Can you linearize that? Get in the form like y equals mx, as in y equals mx plus b, sort of. Right? That's one way you can do it. So that the spring constant is gonna have something to do with the slope of that straight line. All right, so one thing you could do is you could square both sides, and that would get rid of the square root, which would be really nice. I guess it's not 100% necessary, but I think it'd be a good thing to do. Like what you're trying to sort of solve for is get it unburied from the square root. Okay, that's it. You guys get that? And you know what you could do is you could slide this k over underneath the 2 pi squared, right? 2 pi quantity squared. You get 2 pi quantity squared divided by k all times m. Could this be the form y equals mx? When I say m, I'm talking about the algebra like a slope. Y equals slope times x, like that. Okay. How many guys opted to do that? All right, because if you did that, that is exactly what's on this slide. That's one way to do it. Okay. And then if you were asked a question about how would you get the spring constant from the slope, could you set the slope equal to 2 pi quantity squared divided by k? Okay, so the spring constant has something to do with the reciprocal of the slope, right? Okay. That's one way you can do it. That's not the only way. Can you? Who can rearrange this formula so that the slope is exactly equal to the spring constant? So you can just grab the slope and boom, you got the spring constant and you're done. Can you guys do that? You guys will head start. How can you rearrange that so that the slope is k and then you're just done? And there's like no more math to do. Here's okay. You guys good? You guys ready? Here's what I'm thinking. Since the k is in the denominator, which is something to do with like the reciprocal of the slope, maybe I should like flip and multiply this over. Right? Maybe I want my x and y axes to be like swapped, right? Okay. So let me try that. Let's start from scratch over here. I'm going to go m equals, and then take this guy, dunk it upside down over here. Could be k divided by 2 pi quantity squared times the time period squared. And then, how about this? Could I take the 2 pi quantity squared, slide it underneath the time period squared, and go mass is equal to k multiplied by t t squared on 2 pi quantity squared, like that. Okay. This could be y equals mx, or like y equals slope times x. Okay. And now the slope just is the spring constant. Boom, done. Okay. Now the trick there is that the 2 pi quantity squared is embedded in the x-axis, right? So you could get, actually, that is exactly the way I was leading you guys with this one. Again, I wish I hadn't done that, so you could just do the whole thing from scratch yourself. That's exactly what this is. Like mass versus time period squared divided by 2 pi quantity squared. Right, you guys see that? Right. So I bet this is going to result in a straight line where the slope just is the spring constant. Right? You guys can see that? Right. Or actually, if I just backtrack a step to this right here, that could kind of do too. You just have to multiply whatever the slope is. That's the slope right there, right? You have to multiply that slope by 2 pi quantity squared to get to the spring constant. Okay. Or how about this? How about this? I'll show you one more way. Could I take the 2 pi quantity squared and cross multiply it and do 2 pi quantity squared times m, and that could be your y-axis equals spring constant, which is the slope of the line, times time period squared, right? Right. That would also, okay. You could do that too, right? Right. I proved that in this last column. Damn, wish I hadn't done that, but you don't want to do both. You don't want to do time period squared divided by 2 pi quantity squared and also 2 pi quantity squared times mass, right? It's like either or, right? You do one or the other. Okay. But be comfortable with being able to do that, being able to like, rearrange things algebraically so that you can linearize something. It's a skill you got to have to pass this exam. Okay. All right. So let's tables real fast. Hooke's law pretty straightforward. What's the mass? Oh, I should put gravity field, right? Gravity field could be 9.8 meters per second squared you could use, or 10 meters per second squared. Okay, should have done that. G, just do 10 meters per second squared all the way down. Okay, but mass in kilograms would be a good thing to have. So if you get like this guy's 100 grams, this guy's 100 grams, how many kilograms is that?
0.1.
0.1, right, 0.1 kilograms, right? Which would be how many newtons? Pretty close to 1. Yeah, this is about 1 Newton right here. Okay, good call. Okay. All right, you guys can break out the meter sticks, measure this. Okay, that's pretty straightforward. Okay. Now the oscillation one, you guys bring your stopwatches today, get the time period. Okay, just like yes, a couple days back, 10 oscillations and then divide by 10 to get 1 oscillation, right? Which should be right, okay. Right. You guys think you can handle this? Right, you guys think? Right, so I've got some buckets of springs back there. I got some meter sticks. They're all in the lab area. I will walk around and help you guys out. And yeah, when you guys finish, well, see where you guys are. We got a good amount of time. So I'll walk around and help you guys out. You're looking, what's the spring constant? That's your ultimate goal. What is the spring constant of that spring?